Alright, so today we're going to be looking at 5.3, problem solving with combinations. So here we have the little guys trying to solve his problems. So remember, there's many steps to solving a problem. First, identifying what the problem is, analyzing the problem, developing a plan, implementing the plan, evaluating, and repeat. Okay. So there's no real one way of doing things. It's just a matter of finding the tools that you like. So we're going to be looking at how we can use our tools to solve different problems. So first we need to talk a little bit about set theory again. So a set is a list of objects, right? So we can talk about the subsets. So subsets are the number of ways that we can count or group the elements of the set. So the subsets of A is just null set and 1. Subsets of B is the null set 1, 2, and 1, 2. Okay, so order doesn't matter, so this is just one set instead of being two sets. Subsets of 3, since they're 1, 2, 3, are null set 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Okay. So if you're keeping track and counting, combination is simply a subset of a group of n distinct objects. The total number of combinations containing at least one item chosen from a group of n distinct objects is 2 to the n minus 1. So the reason why we subtract 1 is because we said at least 1. So that means we can't have the null set. So that's why we subtract 1 to take out the number of combinations including the null set. So in his pocket, Patrick has a penny, nickel, and a dime. If he wishes to throw one of these coins into a wishing well, how many sums of money are possible? Or one or more. Okay. Since there are 3 items and one needs to be chosen, at least one, then there's exactly 2 to the power 3 minus 1, which is 8 minus 1, which is 7. So there's 7 different combinations that Patrick can throw into the well. Okay. If at least one item is chosen, the total number of selected items from P of one kind, Q of another kind, and R of third kind, and so on is P plus 1, Q plus 1, R plus 1, blah, 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 minus 1. Okay, so these are when we have repeated items or items of the same, undistinguishable items. So for example, a DJ has 5 rock songs, 2 blues tunes, 3 jazz pieces in his playlist. And how many ways can he choose at least one song to play? Okay, there are 5, so we have to add 1 to each of our number of elements. So 5 plus 1 is 6 for the rock, 2 plus 1 is 3 for the blues, jazz is 3 plus 1 for 4. And the total number of combinations of songs the DJ can play, assuming that they play at least one song, is 6 times 3 times 4 minus 1, which is 72 minus 1, which is 71 combinations of songs. Alright, so a little diagram to help you figure out which formula to use, since we've been looking at quite a number of formulas over the last couple of chapters. So, first question to ask, is order important? If yes, then we're going to use a permutation. If no, we're going to use a combination. So let's look at permutations. So can some objects be selected more than once? Yes. And we use the fundamental counting principle. No. Are any of the objects identical? Yes. Use our n factorial over a factorial, b factorial, c factorial, yada yada. Or no. And we just use NPL. Right, so on the combination side of things, are you choosing exactly R objects? Yes or no? Could objects be identical? Are some objects identical? Yes or no? Count individual cases? No. Use NCR? If yes, then use P plus 1, Q plus 1, R plus 1, minus 1 formula. There's no identical objects. Use 2 of the n minus 1. Okay, so this is a chart to help figure out some questions to ask yourself while you're working through the problem to figure out which formula to use. And then use that formula. And there's some homework questions for you to try. I know it's a short lesson, but that's about it. So, if you have any questions, come see me tomorrow before school starts or in class. Thank you. Bye.